Welcome to day 10 of our review, prepping for the AP exam, which is a week from tomorrow. So we still got some good time left to keep practicing, keep reviewing, but it is coming up soon. Remember, do not give up. Keep fighting, keep practicing, keep learning, right? It's all about how you do on that one day, so we want to be as prepared, absolutely as prepared as we possibly can. Okay. Today we're talking about continuity, differentiability, and L'Hopital's rule. These are things, continuity and differentiability we talked about, very early on in the year. L'Hopital's rule we learned a little bit later on how to evaluate limits as kind of a nice shortcut so we don't have to factor and things like that. So let's start with continuity. A graph is continuous if it's connected everywhere, right? We don't have any vertical asymptotes, we don't have any jumps or breaks or anything like that. Let's talk about continuity at a point. Also, keep going through all of these Quizlets. I'm going to add some more things to that Quizlet. The more we review, the more I remember stuff that should be on there. So I'm going to add some things to that. Keep going through it. Go through it until it's absolutely automatic. Those definitions are so important to have down. You'll thank yourself later. Okay. So let's talk about continuity at a point. Here's a definition that we have to know. F of x is continuous at x equals a. At some point, x equals a, if and only if the following things happen. Number one, for a function to be continuous, the limit must exist. So the limit at that point, a. So number one, limit as x goes to a of f of x must exist. Just a reminder on determining whether or not limits exist. Limit x goes to a of f of x exists if and only if the left-hand limit of f at a equals the right-hand limit of a. On the free response section, there's a possibility that you might have to prove that something is continuous. The notation is going to be very, very important there. Make sure you're very comfortable writing a left-hand limit notation, right-hand limit notation to show that the limit as x goes to a of f of x exists. Okay? So that's the first one. So that right-hand and left-hand limit is really important when we're dealing with piecewise functions, right? So we plug in the number into, let's say 3 is the point where it changes, right? One will be x less than 3, one will be x greater than or equal to 3. Right, for the left-hand limit, we plug into the less than sign. For the right-hand limit, we plug into the right-hand sign. And you need to show that explicitly. You can't just plug them both in without the notation. You need that notation right there. So, number one, the limit must exist. Now, if a limit exists, that doesn't mean the function's continuous. It just passes step 1 of our 3-step process. Okay? Step 2. F of a must be defined. Okay? So f of a must be defined. When I plug a into our function f of x, I must get a number out. The third step is we have to show that the limit and the function are equal at that point. So my third step and just looking at the third step by itself That's our definition of continuity. Our definition of continuity is the limit as x goes to a of f of x must equal f of a. This alone means continuity. Yeah. So sometimes they just test you on the definition of it. So if they say, if this is true, what does that mean about f? Well, it means that f is continuous at point x equals a. Okay, let's talk about what happens if these things fail. Let's say that you do a left-hand limit and a right-hand limit and you get different answers. So the limit doesn't exist. Let's say your left-hand limit is 2, your right-hand limit is 3. Well, that means it's discontinuous. But what kind of discontinuity would it be? Well, let's take a look. Sorry. So let's say we see a piecewise function like this. They might ask you, is f of x continuous at x equals 1? Okay. Well, again, to tell if it's continuous at x equals 1, if this was a free response question, we'd have to show our good notation. So the first thing I'd go after is the limit. So first off, I'm going to figure out the limit as x goes to 1. I'm going to figure out the left-hand limit as it approaches 1 from the left side. Well, I'm going to plug 1 into, to do a left-hand limit, I'm going to plug into the one that's x is less than 1. So that'll be 2 times 1 plus 5, which equals 7. For the right-hand limit then, and again, they need this notation. You can't just plug it in without this notation. You have to have these two things. Very important. Shows you really know what you're doing. For the right-hand limit, I'm going to plug into this one, where x is greater than or equal to 1. And I'll get 3 times 1 squared minus 2. That's 3 minus 2, which equals 1. So the right-hand limit is 1. The left-hand limit is 7. They're different. Therefore, limit as x goes to 1 does not exist. Therefore, f is discontinuous. At x equals 1. Okay? So that shows that we are not continuous. It failed step 1, so it fails. What type of discontinuity would this be? Well, when I approach 1 from the left side, I'm getting 7. When I approach 1 from the right side, I'm getting 1. I don't know exactly what my graph looks like. But I know I have something like this. This right here is called a jump discontinuity. Now, let's say I pass step 1, the limit exists, but f isn't defined at a, or f of a is defined differently. Well, that would be that would mean we'd have a hole. Okay. Good. I said I wanted to show you an example. So continuity means that we're connected. Differentiability means not only is it continuous, the graph is connected, but the slopes match up too. Let me show you an example of a problem that you might see. what values A and B for constants A and B make F differentiable. Okay. We saw one like this today in class, but they just wanted to say what value makes the thing continuous. Well, sometimes they'll give us two letters, and they'll say what makes this differentiable. Okay, so we need to come up with two equations here. If F is differentiable at x at x equals 1. If the function is differentiable, that means the function has to be continuous. So the limit as x goes to 1 minus must equal the limit as x goes to 1 plus. So I'm going to say 12a1 plus 5 must be equal to 2(1) squared plus b. Okay? What I'm doing is the limit as x goes to 1 minus, I'm setting that equal to the limit as x goes to 1 plus. So I'm setting the two functions equal to each other and plugging in the number 1. Well, solving that, I get 12a plus 5 equals 2 plus b. Now, I can't solve that for a and b right now. But notice I said that the functions have to be differentiable. The function has to be differentiable at x equals 1. So not only must the functions equal each other at x equals 1, their derivatives must equal each other as well. So let's think about f prime of x. Well, that's going to be the derivatives, right? Well, the derivative of 12ax is 12a. The derivative of 2x squared plus b would be 4x. Again, this is for x less than 1, this is for x greater than 1. So not only must the functions equal each other to give me this, the derivatives must equal each other. So 12a must equal 4x, but x is equaling 1. So I get 12a equals 4, so a equals 1/3. Okay. So that gives me a. Now I can plug in up here, and I'll get 12 times 1/3 plus 5 must equal 2 plus b. Now I can go and solve for b. 12 times 1/3 is 4. So I get 9 equals 2 plus b, and I get b equals 7 for my other number. Not only will these functions be continuous, right? The left-hand and right-hand limits will be the same, but the left-hand and right-hand limits of the derivatives will be the same. Again, this equation came from the limit as x goes to 1 minus of f prime was equaling the limit as x goes to 1 plus of f prime. So for differentiability, we need the derivative limits to equal each other, as well as the limits, the left and right hand limits of f. Okay. We're going to have differentiability problems. We're going to have differentiability problems with corners. We're going to have differentiability problems with cusps. And we're going to have differentiability problems with vertical tangents. All of these problems, all of those places are going to give us difficulty with differentiability. Okay? If they tell you a function is differentiable, that means we also know it's continuous. Okay, lastly, L'Hopital's rule. Okay? When can we use it? We can use it when our limit comes out to 0 over 0, or plus or minus infinity over plus or minus infinity. Okay? Again, if this is a multiple choice, you don't have to really worry too much about your notation, right? But still make sure you check to make sure you have a case where we can use it. If it comes up on the free response, right, there's a good chance they'll ask you a limit question on the free response, and then you're going to have to show that the limit makes 0 over 0, and then you're going to have to say, using L'Hopital's rule, we get this. Okay? What L'Hopital's rule says is that if we have a limit if we're doing a limit of like f of x over g of x, right, if we plug in and we get 0 over 0, then this limit will also equal the limit as x goes to a of f prime over g prime. It's not a quotient rule. Don't get it mixed up with the quotient rule. Just do the derivative of the top and the derivative of the bottom, then replug in. But you have to say using L'Hopital's rule. Let me show you an example. Let's say they asked you to find this limit. Okay? Now, if it's multiple choice, we would just plug in, and see that it's going to be 0 over 0, and we can just do the derivatives and plug in again. Okay? But let's practice this like it's on the free response. Okay? We have to plug in 5 for x. Well, when we do that, we get 25 minus 25, which gives us a 0 on top. And we plug in 5 to the bottom, and we get 25 minus 15 minus 10, which is also 0. So then we say, using L'Hopital's, I'm going to solve this by doing the limit as x goes to 5 of the derivative of the top. The derivative of x squared minus 25 is 2x. And the derivative of the bottom, which is 2x minus 3. Now I can plug in and I get 10 over 10 minus 3, which is 7. So I get 10 sevenths. Okay. Other questions they might ask about this is, what's going on with our function at 5? Well, when we get 0 over 0, we're clearly getting a hole there. So we have a discontinuity. We have what's called a removable discontinuity at 5. But there'd be another discontinuity in this function as well. That bottom factors into x minus 5, x plus 2. So negative 2 would be an infinite discontinuity. We'd have a vertical asymptote at x equals negative 2 in this function. If we plugged in negative 2, we get 4 minus 25, we get negative 21 over 0. And that's undefined in a different way than 0 over 0 is. Example 2. This time our variable is h. So I'm treating h just like I would treat x if it was the limit as x goes to 0. Okay. So again, I need to think, what's going to happen when I plug in 0 for h? Well, pi halves plus h is going to be, or pi halves plus 0 is going to be pi halves. I'm going to get sine pi halves minus sine pi halves. That's 0. Over 0. I get 0 over 0. That doesn't mean the limit doesn't exist. It just means we're undefined right now. Okay. So what can we do? Well, we can use L'Hopital's rule. say the limit as h goes to 0. So now I'm going to have to do the derivative of the top and the derivative of the bottom. Now, h is my variable here. The derivative of sine of pi halves plus h, that's going to be a chain rule. That's going to be cosine of pi halves plus h times the derivative of h, which is simply 1. How about this? The derivative of sine pi halves. Be careful. That is just a number. It's not cosine pi halves. It is 0. And the derivative of h is 1. So basically, I just get cosine of pi halves plus h. Now, plugging in 0 for h, I get cosine of pi halves, which equals 0. 0 plus 0 equals 0. So here my limit equals 0. Okay? So that's just a reminder on continuity, differentiability, and L'Hopital's rule. Be careful with these ones. Oftentimes this is a constant, so just know that the derivative of a constant equals 0. This usually will have a chain rule. Okay? The chain rule ended up not really being a big factor here, but it can be. I will see you guys on Wednesday. Talk to you later. 2 chains, bye.